Welcome back to Honey of Knowledge. So, in this edition of MSQE mini lectures, we will be continuing the discussion on econometrics. Now, so far, we have covered the magical equation of econometrics, y is equal to a plus bx plus e, and we have also understood how to plot a scatter diagram and how to look at the scatter diagram and find its correlation, and how to infer whether this correlation is giving us an idea that this magical econometric equation can be used or not. Now, how do we estimate the values of a and b? So, to get the essence of this, what we need a kind of line passing through these points on the scatter plot. Now, to find out this line, what we need is a line which minimizes our error. And what is the error in this situation? This E. So to minimize E is the same as finding the line of best fit for this scatter plot. How do we minimize this? If you just rearrange the terms over here, you will get E is equal to y minus a plus bx. Just take this thing over here. So what will be y minus a plus bx? Let us suppose you have estimated the values of a and b. So in that case, a hat and b hat will be your estimated values of a and b, and e will also have a hat because you have estimated one side of the equation, so the other side has to be necessarily have the same reflection. You can never compare apple to oranges. So this is the guy which we have to minimize, because when we want to minimize E, in effect we cannot minimize E, we will be minimizing E hat or the estimated E. Now what is the value of E hat? Let's check that. So let us suppose this is the line a hat plus b hat x. So if this is our line of best fit, what is y minus this thing? So take any point x over here and do a construction. The dotted line meeting this line of best fit will give you a hat plus b hat x. And if you take the dotted line up above, you would find a point on the scatter plot, and that point will be your xy. So if you take the y coordinate, it will be y. So what is y minus this thing? This essentially is this guy, the difference in the y coordinate at x of these two corresponding plots. One, the scatter plot, the other line of best fit. So you could think of it in this way, that you have a scatter plot on xy graph and you have a line of best fit. And for every value of x, you will have a y corresponding to the scatter plot and a y corresponding to the line of best fit. So you find a difference, and that difference is your E hat, or the estimated residual we call. So just to give you a new terminology over here, E is also known as residual. This is estimated residual. Estimated residual is the difference between the y values between scatter plot and the line of best fit, and we have to minimize this E hat. Our task is to minimize E. In order to minimize the residual, we need to find a system, a methodology. As you will be having n observations, you need to minimize residual for all the n observations combined. You cannot minimize it for just one value of xy. So you need to find out a system for all the points. So for that, what we do is we minimize summation ei square, which is equal to summation yi minus a plus bxi whole square. Now there are 2 points over here. One, we have already talked about that we need to do it across all the points. That's why summation. And we need to do it in such a way that the positive deviations, the scatter plot would be in such a way that there would be points above the line of best fit and below the line of best fit. If we consider both these kind of points, one, we will get positive as well as negative deviations. So in some way they could cancel each other out. And in that way, we will be not getting a true representation of the error. We don't have to have a bias on error. We either need a positive error or a negative error. So we can either transform all the errors to a negative sign or to a positive sign. And it's easier to deal with positive numbers in algebra or any kind of mathematical analysis. So we try to find the error in positive terms, whether the point is above the line of best fit or below the line of best fit. We need to do the analysis in such a way that all those points are considered the same for error perspective. That is why we take the square. The moment we take a square, the positive negative deviations become one, just deviation. That is why we take summation as well as square. Now this is the thing which we need to minimize, and whenever we have to do this kind of an optimization exercise, this is a pretty simple question on calculus. We differentiate this once, and that is your first order condition. And what are the things which are changing? Remember, x, y are not changing over here. We are trying to find a and b, so we need to change a and b to find the minimum of this. So we need to change a and b and find them accordingly. So we need to differentiate this with respect to a and b. Let us go ahead with that. Del summation ei square with respect to a will be equal to, this square thing will get out. Now to think about it, so you have this thing square for first point, then this thing square for second point, then this thing square for third point, and so on for n points. So if you take all these individual terms and differentiate them, for all those terms my 2 will come out, and when you take that together again, you will again get the summation and 2 will come out common across the terms. So you can write 2 summation yi minus a plus bxi, and this must be equal to 0. Now you could ask that what about the inside term, because in chain rule we need to go inside the function. When you go inside, a has no coefficient, so differentiation of any variable when it has no coefficient, x for that matter, differentiate x with respect to x, you will get 1. So differentiate a with respect to a, you will get 1. So that is why you don't need to bother to go inside here. This should be equal to 0, the first order condition. FOC we call this in economics. And a bit of modification, you will also have a minus sign, which is inconsequential because you are equating it with 0. Minus sign because a has a minus in front of it. So let's go to b now. Del summation ei square upon del b will give you, again 2 will come out, 2 summation yi minus a plus b xi, and now you need to look inside. B has a coefficient of xi, which means it will have x1 for the first point, x2 for the second point, and so on. So xi will be inside the summation, and also b has a negative sign similar to a, so you'll have a minus sign over here, and summation will also contain xi. This should be equal to 0, FOC, first order condition. Now these two equations are known collectively as normal equations. You can also think of normal equations in a slightly different way. What is this guy over here? This guy over here is your EI, the residual of ith point. So you can write summation EI equal to 0. You don't need to worry about minus 2 because minus 2 into something is equal to 0. So definitely this something is 0 because minus 2 cannot be 0. If you come here, you have EI into XI, and again you can forget minus 2 over here. So summation EI into Xi is equal to 0. So this is an alternative way to write the normal equations. Let's look at the utility of normal equations now. Expected value of estimated residual or the average value of estimated residual is equal to 0. You may ask, why so? Let's look at that. Now, how would you find the average value of estimated residuals? Estimated residuals EI hat will be equal to YI minus A hat plus B hat XI. I have used hat throughout. Reason being, the moment you estimate the values of A and B, they no longer remain A and B, they become A hat, B hat. And once you use A hat, B hat, E also has a hat. Now, if E has a hat, you'll have to think in terms of estimated values. So even in the normal equations, you need to write E hat. Now, you don't need to worry about X because X is a known value. You are not estimating it. If I want to find the average, what will you do? You will sum it up and divide the number of observations. But I already know what is the sum of this guy. It is equal to 0, normal equation. So this is equal to 0. So the average value of residual or estimated residual is equal to 0. The expected value of estimated residual or the average value of estimated residual would be equal to 0. This is one application or utility of normal equations. And before we go to the next set of utilities, we need to estimate value of A hat and B hat. So let's estimate the values of A hat and B hat. Rewriting these normal equations, you will get yi minus A hat minus B hat xi is summation equal to 0 and summation yi minus A hat minus B hat xi into xi equal to 0. Let's rearrange the terms over here. This can be further simplified. Let's rewrite them in a slightly better form. This is a pretty standard linear system of equations in two variables, A hat and B hat. If you have some difficulty in understanding this simplification, I'll give a bit of hint. When you're summing up A hat over the n terms, you will have n into A hat. So I have divided the first equation by n throughout. So you will get a term free of n over here rather than n hat. But n will come in the denominator for the other two terms because they don't have n. Similarly, if you go to the next equation, A hat is a constant for us when we estimated. So A hat will come outside the summation and you'll have A hat summation xi, and I have divided whole throughout by summation xi. That is why what n is doing here, summation xi is doing here. After that, the steps are quite easy. I mean, I'll give you a head start to this. Just put a minus sign over here this will be cancelled, you will get a value of b hat, and if you plug in this b hat again into equation, you will get the value of a hat. I won't do this exercise because it's pretty easy in nature, and you will get the final result as understanding a hat is pretty standard or easy. This is your y bar, the average of y. This is your x bar, the average of x. So you write y bar minus b hat x bar. But you are still left with finding out b hat. So let's find out b hat. How do you get the b hat? As I said, upon simplification, you will get these two values. So this is your b hat. Now, this looks quite intimidating, but this is not. I'll give you a bit of recall on elementary statistics. Covariance of xy is equal to expected value of x into y minus expected value of x into expected value of y. Now, expected can be thought of as average. If that is the case, this thing is average of xi yi, or simply the expected value of xy, and over here I have expected value of x and expected value of y. So the numerator can be thought of as expected value of xy minus expected value of x into expected value of y, or simply the covariance of xy. And if you look at the denominator, I'll give you again a bit of recall on statistics. Variance of x is equal to expected value of x square minus expected value of x whole square. And it goes without saying that this is equal to this, because this is the average value of x square or expected value of x square, and this is the square of the expected value of x. So in effect, you will have b hat is equal to covariance of xy upon variance of x. So now you have a hat as well as b hat. So let's jump into the next set of properties. Next is covariance of e hat x is equal to 0. Let's understand why. If we rewrite this as summation of ei multiplied by xi upon n, recall the earlier definition of covariance, minus summation ei upon n into summation xi upon n. Whenever you have to find covariance of two things, multiply them and find the expectation, and then find the individual expectation and then multiply them. Now this guy, upon simplification, is going to give you this quantity. Now I got this upon just expanding upon this. I have substituted the value of residual ei as y minus a hat minus b hat xi, and then just do a bit of multiplication. Few terms will be cancelled out, and you know what is variance and covariance. And then after this, you know that b hat is this quantity. So let's just plug in b hat from here to here. Now b hat is covariance xy by variance x. So b hat into variance x is covariance xy. So this thing over here, b hat into variance x, is going to give you covariance xy. So this thing will be your covariance xy, which will be getting cancelled by this quantity. So this becomes 0. So LHS is equal to RHS. Hence covariance between E hat and X is equal to 0. Let's go to the next utility of normal equations. Covariance of E hat Y hat is equal to 0. Now this is Slight modification. In place of x, I have y hat. Now, how do we prove this? In place of y hat, we can write a hat plus b hat x. So the moment you want to find out the covariance between these two quantities, what you will get is covariance of e hat and a hat plus b hat x. Now a hat and b hat are constant values, the estimated constant values. So it will be equal to 0. This result has a very important application. Let's look at that. When we have y value, it is equal to y hat plus e hat. So whenever you want to find the variance in y, you need to find the variance of this quantity. Let's expand it. You will get variance of y hat plus variance of e hat plus twice of covariance between e hat, y hat, and I already know that this guy over here is equal to 0 based on my earlier result. So variance of y can be simplified into variance of y equal to variance of y hat plus variance of e hat. Now if you look at this equation carefully, the explanation of y or the prediction of y based on the model is explained by y hat and is unexplained or remaining to be explained due to residual or e hat. So this is the explained part, this is the unexplained part. If we divide this whole throughout with variance of y, we will get 1 is equal to variance of y hat upon variance of y plus variance of e hat upon variance of y. If you match up these two things, you will understand that this is kind of a proportion of variance explained due to the model, and this is the proportion of variance which is remaining to be explained because the sum of these two numbers is equal to 1. So this gives you a kind of restriction on the model, the explained part and the unexplained part, and we will be talking more on this in the next set of videos, and we will be also doing multiple linear regression. Multiple linear regression is simply expanding one independent predictor x into x, z, w and so on. In other words, rather than just having one predictor of y, we will have multiple variables predicting y, which is always better. It's better to have more predictors than a single predictor. So we will be talking about multiple linear regression, and we'll be moving towards more linear algebra dependent econometrics in future set of mini lectures. So that's it for this mini lecture. This may be kind of heavy for you in the beginning, but if you rewind this video and play it on the portions you found difficult, it will sink in. And you don't need to be worried about this because it is a bit tricky in nature in the very beginning, but in the later stages you will find it very easy once we start with the linear algebra treatment of econometrics. So we will catch up in the next lecture of econometrics. Till then, bye, and don't forget to subscribe to this channel and hit that bell icon and also like.